Welcome to this chemistry lecture series. In this lecture, I am going to cover the module 4, that is unit 4, polymers, uh, particularly the macromolecular chemistry or the polymer chemistry for the first year BTech chemistry students. So I am going to present this lecture in two parts. So I will split this into two parts. The first part I would like to cover up to addition polymerization. So let's see the basic definitions. As you know that polymer chemistry, we study a lot of polymers, conducting, non-conducting, and macro um, macrocyclic polymers, and many types. So first, before getting into the topic, I would like to introduce the terminologies to you. Let's see what is the word polymer. Polymer is derived from the Greek words poly and meros. Poly means many and meros means parts. So the many parts, like a single unit, that when it is repeatingly, then it will form many units, right, connected together. That will constitute a polymer. In simple words, you can say polymer is a substance that is composed of molecules that have long sequences of one or more specific species of atoms or groups, or a group of atoms linked to each other. How? Through covalent bond. So mostly in the polymers you will see only covalent bond. So they are very strong and rigid, and they have different physical and chemical properties. So like ethylene, let's take a simple alkene, that is n moles of ethylene. Then if you react this with peroxide at 120 degree to 200 degrees Celsius, then this unsaturated double bond will be, polymerization will happen, and it will be converted into single bond, which means this is a single monomer unit, NCH2 double bond CH2. So this will be repeating along the right as well as on the left. So I have put this N. So if you are taking N molecule, that will be attached on both sides, and it will form a polymer chain. So this is a simple example for the linear chain polymer. So before 1920, in the 19th century, the polymers are considered as physically associated aggregates. So there were no proofs regarding their chemical association or chemical linkages or covalent linkages. In the year 1920, Hermann Staudinger said that polymers are composed of very large molecules like macromolecules containing long sequences of simple repeating units that are linked together by covalent bonds. So he is the one who first identified that the simple units are not simple units, but they are actually long sequences of simple units which are linked together by covalent bonds. So this is how the history of polymers started. And also in 1920, Staudinger introduced, he was the first to introduce the word macromolecule to describe the polymers. He got the Nobel Prize in 1953. After 33 years of this discovery, he got the Nobel Prize for the polymer chemistry. Sometimes polymers and macromolecules are used interchangeably in the field of polymer chemistry. Macromolecules. So we should know the difference between a macromolecule and a polymer. Macromolecules are materials, especially large size. Look at this one. The structure on your right is a macromolecule. It is not a polymer. It is lignin. So lignin is derived from wood, natural wood. So can you see this one, this aromatic skeleton? It is this structure is having lot of repeating units like OCH3, ether bonds are present, and also COCH3, methoxy groups are also present. So this is repeating, like how I can say, like if you see a tree, there will be a lot of branches, no? So like that, if you see a parent one, then this is branching out extensively to form large branches that looks like a macromolecule. In simple terms, we can say a plant and a tree. So the monomer unit will be like a plant or with one leaf or two leaves. But tree will be like a macromolecule with a lot of branches. So in that way, you can understand the difference between the monomer and the macromolecule. And while polymers also have larger size, look at this one. For example, if we are taking one monomer unit, for example, let's take ethylene. So you got CH2, double bond CH2, two carbons and two hydrogen. We know that carbon atomic mass is 12, hydrogen atomic mass is 2. Two carbons means 24, two hydrogens means 2. 24 plus 2, 26 is the molecular mass of ethylene. If it is polyethylene, then 26 is the ethylene molecular mass. Now, if you are having 10 chains, ethylene chains linked together, obviously 10 into 26, 260. So the molecular mass of the polymer will be higher than the molecular mass of the monomer. So that is what I have mentioned here. Polymers also have larger size, so, and high molecular weight. So you can determine the molecular mass of a polymer by gel chromatography, that you know. But it also consists of repeating molecules. So that is the reason why it is having massive chemical structure and high molecular weight. So polymer is formed by macromolecules in principle. So all polymers are macromolecules because they are having a lot of repeating units and they are massive molecules. But all macromolecules, for example, lignin. So this lignin is a macromolecule, but it is not a polymer. That's why they call it as all macromolecules are not polymers, but all polymers are macromolecules. Polymers equal to macromolecules, but macromolecules is not equal to polymers. Okay, so you should also know about some terminologies like monomer, polymerization process, degree of polymerization. So the repeating unit in a polymer by which a polymer or macromolecule is formed is called monomer. Something like simple building block. So you might have played the building blocks now. You will be constructing a large building from a small building block. So that one single unit is called a monomer. And whatever that, if the same building block is repeating means you will get a massive structure, that is polymer. So this process you are building with your hands now, like monomer to the massive um, building structure. So that is polymer. That process, how you are building that process is polymerization. Same way in the monomer units in aqueous solution also, they connect with each other through the covalent bond and they keep building up, and that entire process is called polymerization. This polymerization is governed by pH, temperature, and the monomer concentration, and many more parameters will come into play. And when you are doing a polymerization in a laboratory, you have to take all these things into account, and you have to do the polymerization. And there are several types. We will see the types of polymerization in the coming slides. And what is meant by degree of polymerization? The number of repeating units in the polymer is known as degree of polymerization. So if you have ethylene unit, monomer I told now, if 10 repeating units, then the degree of polymerization is your number of repeating units. So the number 10 is the degree of the polymerization of that particular polyethylene unit. Okay. So the most basic requirement for polymerization is that each molecule of the monomer must be capable of being linked to two or other molecules of the monomer. How? By chemical reaction, which means that monomers must have a functionality of two or higher. So this is what called functionality. So are you able to follow? The basic requirement for polymerization is each molecule of that monomer must be capable of being linked to two or more other molecules by chemical. So the fundamental criteria, the minimum criteria, it should be connected with the two other molecules. So the minimum functionality will be 2, the maximum functionality can be more as much as possible. Okay, let's move on to the monomer functionality and the polymer skeletal structure. For example, the functionality, as I told you, the functionality of a monomer is the number of chain links it can give rise to. If it can give rise to 2 chain links, then the functionality is 2. If it can give rise to 4, the functionality is 4. That's simple. It is not necessarily equal to the number of functional group. For example, functional group you all know: carboxyl group, carbonyl group, and different functional groups are there, right? So you should not count that functional group. You should only count how many number of chain links it can give rise to. That is the functionality. Okay, and let's move on to the next one. Polymers formed by chain polymerization of olefinic monomers should contain a single carbon-carbon double bond. So ethylene is an alkene or an olefin. So it is formed by this chain of polymerization is formed by this olefinic monomer, that is ethylene, containing a single carbon-carbon double bond. These monomers, as a result, this can give rise to one chain on the right and one chain on the left. As a result, the functionality is 2. Okay. Uh, if a monomer has a functionality greater than 2, then this will lead to obviously the formation of branches, and possibly a network type polymer can be formed. This all depends on the particular polymerization. So which polymer, like addition polymerization or condensation polymerization or free radical polymerization, it all depends on the particular polymerization. Now let's see this linear polymerization. Can you see this one? There is a square in the middle, and two points, connecting points are there. So the functionality will be 2. Am I right? 2 ends it can form. And then this linear polymerization will be going on like this. So do you, in real world example, if you see the train couches, one after the other, they are one compartment to the other compartment, it is attached now. So when we are playing the train, when we are kids, so you might have connected one compartment to the other like that, like connecting in a linear fashion like that. And also we also have the garland or beads, right? So when you are connecting one bead next to the other like that, so you are arranging it in a linear fashion or in a straight line. So that accounts for the linear polymerization. So polyethylene is the best example for linear polymerization. And what is meant by branching polymerization? So let's take the same building block or the monomer unit, so which is represented by a square and two connecting points. And also, if you are reacting with this type of monomer, that is with two connecting ends, with a monomer that is having three connecting points, as a result, other than growing linearly like this fashion, it can also grow vertically and again horizontally also. I think this you might have played in a video game, right? Like a snake game. So in that one, it will be coming um, each branch or something will be coming, and then it will be connecting. Or the snake will be trying to eat the food. I think you may remember. So the chain will be keep on growing in that fashion. So both horizontal and vertical direction, the branching will be happening. So that is called branching polymerization. So branching polymerization can either happen between two different monomer unit or single monomer unit with three connecting points or three functionality. So here one monomer with two functionality and the other one with three functionality. So similarly, a single monomer with three functionality can also initiate the branching process, and you will get a structure like this. Similarly, four connecting points also, which is called as, so the one with two functionality is called as a difunctional monomer. This is a trifunctional monomer. This is also an example for trifunctional. So now instead of taking di and trifunctional, you can also take di and tetrafunctional monomer. In that case, you will get even more elongated branches. Can you see the two horizontal chain, longer chain, and also two vertical chains, and some short chains can also grow for, and then it can stop after a point. So whatever this square and this one is called link formed by polymerization, which is covalent bond. I think this is very simple to follow. Okay, and then like I told you, now Legos or you might have played, so you can connect this structure in any form, like a ring or like a plus or something like different structure. So this is also another form of plus, or like a rectangle or a tilted like a pentagon also you can make it, or like a chain, linear chain, different versions. Legos you can create. Now same thing only we are doing with the linear and branching polymerization. Remember, all depend on the functionality of the monomer, whether it is di, tri or tetra functional. And Let's move on to the classification. So in BTech first year, in the unit 4, like CTs, usually this question is asked. So what do you mean by polymer? And then degree of polymerization and molecular weight of polymer, or the classification of polymers. How can you classify the polymers? So there will be a flowchart in the follow-up slide. I will show that one and we can continue our discussion. For instance, you can classify the polymer based on the origin or source. So from where this polymer is naturally procured, or where it is originating from, or where we are sourcing from. So basically depending on the origin and source. And the skeletal structure also matters, whether it is linear or branch, that we will see. And the molecular force of interaction, how this polymer is formed and what type of molecular force interactions are involved. Let's look at this chart. So here, the classification of polymers have been listed based on the source and origin. So polymers can be generally classified into three major types. One is natural, semi-synthetic, and synthetic. For example, natural polymers are found in plants and animals. This includes examples such as proteins, cellulose, starch. So these our body contains proteins and plants contain cellulose and starch, and some resins and rubber also contain the polymeric structure. So this is the protein structure, okay, and this one is a starch structure. You can look at the functionality, and also this ring structure, cyclohexane ring structure is also present with the epoxide bonds. And also semi-synthetic, which means it is not naturally prepared, but some chemical modification we can do with the natural polymer. Like for example, you can take cellulose and you can do acetylation reaction, which means you react with acetic acid and you get cellulose acetate. So that is what called rayon. So we use for fabrics, no? So that is a semi-synthetic polymer. And also cellulose nitrate or nitrocellulose, a nitro group is attached. So you are taking the original or natural cellulose and you are treating with introducing nitro group, and you are preparing nitrocellulose. Synthetic polymer. So these are the polymers directly synthesized from monomers by chemical reaction. The well-known example for synthetic polymer is nylon. We know nylon ropes, right? So that is prepared synthetically in the lab. So neither naturally and not chemical modification, but entirely chemical modification in the laboratory. So that leads to synthetic polymers. These are also called as man-made polymers and are extensively used in daily life. Like we have the polymer chairs, no? We use in our polymer or fiber chairs that are also made of some polymers. Okay, and they have more industrial application. For example, here you are taking adipic acid, which is a 6 carbon molecule, CH2 4, so 4 carbons present in this methyl group, and then 2 carboxyl groups. So 6 carbon. That's why it is called as nylon 6,6. Why? Because it is you are taking a monomer that is containing 6 carbon atom, and then hexamethylene diamine. So you are taking this adipic acid with the carboxyl group and the diamine molecule, that is hexamine diamine. So you are having 6 carbon atoms, right? So that's why nylon 6,6. And this amino group, obviously, this will react with this hydroxyl group and will undergo condensation reaction, and water molecule will be eliminated. And when carboxyl group and amine group are reacting, means an amide bond will be formed. CONH will be formed, and it is more stable. So this is one kind of chemical cross-linking, and this process, one water molecule is removed. So that's why it is called condensation polymerization. And now we are done with the classification of polymers based on their origin, right? Now let's move on to the classification of polymer based on skeletal structure. So how the skeletal structure you can classify, either the polymer can be with the linear chain, or it may have branched chain, or it can be having cyclic structure, or network or cross-link structure. These are the four types of polymers which we can classify based on their skeletal structure. So linear fashion, we already know polyethylene, and polyethylene imine. So here you are having NH bond, that is imine bond, that will be branched out. So can you see this one? This is polyethylene. This is highly water soluble. Although this polymer is branched, it is highly water soluble. And cyclic molecule, this is also present in nature. Cyclodextrin, beta cyclodextrin, that is a well-known compound polymer of this type. And network or cross-linked polymer, this is nothing but phenol formaldehyde resin is called backlight. So aldehyde group and hydroxy group will be reacted, and then you will get this methyl group formed or interlinking the two aromatic rings. So that is how it is a cross-linked polymer backlight. This is widely used in switches and the switchboards we used to make. And the third type of classification is classification of polymers based on molecular force interactions. So what would be the molecular force and how they can be arranged? So let's see their classification. Majorly, we can classify the polymers based on the molecular force of interaction into three types: thermoplastics, elastomers, and thermosets. This thermoplastic can be again classified into two types. One is crystalline and amorphous. Let's see what is meant by thermoplastic. Often this is called as plastic. So these are linear or branched polymers which become liquid, which means they melt upon the application of heat, and they can be, once they are melted, they can be molded or remolded into any shape. You can make it like a ball, or you can make it like a sheet. For example, polyethylene, polypropylene, nylon, polystyrene. That's why nylon we are able to make ropes. So you can heat it, apply heat or supply heat energy, melt it, and then you can mold it into any shape depending on the shape of your mold. Okay, they have both the melting temperature and glass transition temperature. In the polymers, this glass transition temperature is one of the important property, where the amorphous will become crystalline, or the transition will happen. Crystalline state it will be converted to, that is at a particular temperature. So which means when it is turning into crystalline, it will reach a hard or glassy state to a soft and leathery state. For example, if you are heating a polymer at a particular, like 400 degree, 450, if that amorphous polymer changes to crystalline state, or from a hard and glassy state to a soft and leathery state, that particular temperature is called glass transition temperature. This is one of the important property of polymers, and which helps to widen their application. And elastomers, these are the type of polymers which are cross-linked rubbery polymers that can be either easily stretched into high tensions, and they can rapidly recover their origin, like a elastic band, rubber band. So you can apply, you can extend it to certain limit, and when you leave that force or take out that force, then again it can come back to its original position. That all depend on the stress, stretch, stress, and the release of the stress. So when the applied stress is released, then they can come back to the original position. Why? Because the cross-linking density is less. Whenever the polymer change the branches, if they are not cross-linked, they can, when you are stretching, then that polymer can come back to its original state. So this is how stretchable polymers are made with less or low degree of cross-linking. So they can degrade rather than become fluid upon application of heat. Example would be rubber, polysiloxane, silicone rubber, and polyurethane. Polyurethane sponges and all, like packing sponges. Thermosets, these are compared to thermoplastic and elastomer. These are something rigid materials and are network polymers. They have chain motion, but the chain motion is greatly restricted. Why? Because the chains are intercross-linked with each other, or the degree of cross-linking is very high. As a result, the chain can't move freely, so that they maintain a rigid structure. They degrade rather than become fluid upon the application of heat. For example, in the case of the chairs and all, they use highly cross-linked polymers, and the switches also they use highly cross-linked polymers, because once it heat up, it should not melt. At least it should withstand certain temperature. The other example would be vulcanized rubber. So what do you mean by vulcanized rubber? If you have rubber chain, butadiene chain, that chains will be cross-linked by sulfur. So whenever you are introducing sulfur to cross-link between the chain, then that will have high rigidity. And also I told phenol formaldehyde resin, backlight, epoxy resin. These are the highly cross-linked polymers and they are generally insoluble. So the cross-link in chemistry is very, very interesting, and you can make different materials or more strong and rigid materials by playing with the degree of cross-linking. Okay, introduction to stereochemistry of polymer. So this is something important. Why? Because this they often ask in the like in the polymer chemistry itself. This topic is important, but especially for first year BTech student, this tacticity they have asked many times in the like the CTs and also in the final sem exam. So you should know well aware of this topic. Okay, not only is the skeletal structure and the chemical composition of the repeating, but the molecular microstructure can also strongly influence the property of a polymer. We are moving, scaling down from the macro or bulk property to the micro property or microstructure. We are going to look into that. So that particular molecular microstructure can also strongly influence the property of a polymer. We will see how it can influence. Which means the microstructure means the geometric and spatial arrangement of that particular function group or configurational arrangement of the atoms in the repeating unit. So you will have a repeating unit. In that repeating unit, you have certain atoms that will be repeating in the geometric or having certain geometry or configurational arrangement. So when it is changing, then obviously their property will change. So that the distribution of this different spatial arrangement in the repeat units, that is chain, are of particular importance. Okay, who first introduced the term tacticity? Nata is the first to use the term tacticity to describe possibly different structures of a polymer, different possible structures of a polymer. Tacticity is nothing but arrangement of pendant groups of a polymer in space. How this repeating groups or the pendant groups, which means attached at the end, are distributed in the space. A pendant group is nothing but a side group in the main chain. It's a group of atoms attached to the backbone chain of a polymer. So the polymer backbone will be the main chain, but from that you will have a side chain having a group of atoms. That particular group is called pendant group. There are three types of tacticity: isotactic, syndiotactic, and atactic. So this is what you have to write when they ask about tacticity and types of tacticity, and you have to write the types. First you have to explain what is tacticity. So this is the relative stereochemistry of the adjacent chiral center within a macromolecule. What do you mean by chiral? Which are non-superimposable. Already seen this in the geometric isomerism of coordination compound. So you know very well about this. And the mirror images. You have a molecule. If you put the mirror and you get the mirror image, that should not be superimposable, or in other words you can say non-superimposable. Human hands and feet, like left uh, hand glove will not fit in the right hand. That is a simple example. Okay, the simplest chiral molecules have sp3 hybridized carbon atom, which means that to that a particular sp3 hybridized carbon atom, four different groups are attached. That is what means chiral. So you will have a carbon atom at the center and four different groups. For example, you will have one aldehyde, you will have one hydroxide, you will have one methyl, and you will have one carboxyl group. So aldehyde, hydroxyl, carboxyl, and methyl, four different groups attached with the carbon. Then you call it as a chiral carbon. Okay, um, which make the carbon atom asymmetric. Look at this example: two hydrogen, X and Y. So here X and Y are two different substituent groups. So to keep this concept simple, I have taken ethylene, that is CH2 double bond CH2. In that, the hydrogen has two substituent groups. It can be bromine, it can be like chloride, different substituent groups, or methyl. Then this particularly this XY arrangement will change vary throughout the chain. how this XY arrangement in the, which means the substituent group arrangement in the chain, that is spatial arrangement, now distributed in the space changes, that contributes to the tacticity. So this leads to three different types of tacticity and polymer types. Isotactic polymer. Look at this one. So this is how the XY substituents are arranged. In isotactic, look at this XY, that is wedge bond and dotted bond. So both X and Y, the dotted bond is facing away from the viewer. The wedge bond Y is facing toward the viewer. The same spatial distribution is arranged throughout the chain. Similarly, H, this CH2, na, CH2 double bond CXY, na, XY pattern is also repeating same. Whatever the hydrogen atom away from the viewer is repeating the same, and then toward the viewer is also repeating the same. So the spatial arrangement is same throughout in the all repeating units of the same configuration. So that is called isotactic. Symbiotic polymers. So this symbiotic means alternate. You can say the other word alternate. So the configuration will alternate. The substituent group will alternate from one repeating unit to the other. For example, YX, then it is alternating XY, then XX, YX, then XY, YX. So it is alternating. So don't bother about HH because both are same groups, right? Same hydrogen atom. Atactic. So this repeat unit does not have any patient. So irregular or random placement of two configurations. For example, you will have XY. Alternate means it should have YX. Then you should have XY, no? But it is again YX. Then XY. Then YX. Then XY. So it is randomly distributed. That is why it is called as atactic polymer. So this tacticity is a very simple concept, and you have to write this what do you mean by tacticity and three types and give these three examples. Okay, and now when you are doing a polymerization, homopolymer is something also you can't avoid when you are preparing a polymer. So we should also know the difference between homopolymer and a copolymer. Homopolymers are those polymers that are made with one species of monomer which repeat throughout the polymer. For example, you are having the monomer unit A in the chain. So this A will itself will be repeating continuously, and you will get this will be equal to AN. Similarly, the simple example would be CH2. The CH2 is a A type. So this CH2 will be keep on repeating without any alteration in substituent. That is called a homo polymer. Polyethylene is a simple example, a well-known example for homopolymer. Then what do you mean by copolymer? Co means two. So more than one repeating unit will be present. So it can be two or more. So polymers those contain two or more different types of repeat units are called copolymer. Polymers formed by two different monomers. Then it means you won't have only A, you will also will have B. So AN, BM. So this will be repeating. So we have already seen adipic acid and then ethylene diamine. We have seen the HMTA that forms nylon. So you have A the adipic acid, B is in the hexaethylene diamine, that six carbon both nylon 6 6, that reaction you remember. So in that case you will get the amide bond form now. So this is an example for copolymer. So when they ask you about copolymer, you can write the nylon 6 6 reaction. So the classification of polymerization reaction. Now we have done the classification with the nature, structure, linear or branch, and also the interaction we have done. Now we are going to discuss about the types of polymerization reaction. So in this lecture, I will cover up to addition polymerization. But there are two major types of polymerization. One is addition polymerization. Other one is condensation polymerization. Addition polymerization is the polymers with repeat units have identical molecular formula to those of the monomers from which they are formed. So the molecular formula should be same in the polymer and the monomer. For instance, ethylene and this one. What does it mean? So no additional molecules are removed. Just they add together. One ethylene will attach with the other. So the chain will grow on the right side and the chain will grow in the left side. So you will get polyethylene. Condensation polymer means, so this yields polymer with repeat units having fewer than the monomer. Why? Because some molecules are eliminated, like water or HCl are eliminated. So I told you, now you take adipic acid and hexamethylene diamine. So 6 methylene group, and here also 6 carbon. Look at here, 1 and then 4 carbon in methylene group. So 5 and 6. Here also 6 methyl group. So nylon 6 6. So this is also a copolymer. You should remember. I told you now more than one monomer unit. So adipic acid and hexamethylene diamine will react. Here condensation reaction will occur, which means the OH from this one and hydrogen from this NH will condense to form the covalent bond, that is amide bond, which is more stable, and then one water molecule will be removed. So this product is called nylon 6,6. And then when they, this is also an important question in polymerization, polymer chemistry, the difference between addition and condensation polymerization reaction. For example, the addition polymerization, we know that it contains unsaturated monomer unit with double bond. So this involves condensation polymer involves monomers that are bifunctional or trifunctional, which means functionality will be 2 or 3. So the chain will grow, and no elimination of simple or small molecules like water, HCl or methanol occurs. But whereas in condensation polymerization, we already see nylon 6, one water molecule is removed. So like that, water, HCl or methanol will be eliminated. And addition polymerization, also polymers contain identical number of atoms than the monomers reacted. So whatever the n number of monomers you react, you will get n number of polymer molecules. But whereas here, there will always be n minus 1. If something is eliminated, then obviously the polymer contain less number of atoms than the monomers reacted. This can be described by the chain growth. This can be described by step growth. The condensation can happen in one step or two step or multiple steps. So the condensation polymerization will be step growth polymerization. The example for addition polymerization would be polyethylene from ethylene, and here nylon 6,6 from adipic acid and hexamethylene diamine. Okay, so examples of addition polymers or polymerization. I would like to, for this question, we can take 4 addition polymers. We can see their reaction, write any 2 properties and applications. Mostly they will ask to write a brief note on any two addition polymerization, explain their properties and uses. Questions can be like that. So the polytetrafluoroethylene Teflon. Teflon is the one of the widely used polymer, like the pipes and other O-rings. They used to wrap up with this one. This is highly hydrophobic, so it can repel water. So Teflon has lot of application. And polystyrene. Polystyrene fabrics are also used. Polyvinyl chloride pipes, whatever for the electrical pipes we are using, the insulation pipes, that also made of vinyl chloride. And polypropylene. Polypropylene bottles are available, tubes are available. So these are the 4 major additional polymers. We will see one after the other. First, I would like to discuss polytetrafluoroethylene or Teflon. It is obtained. We know that the monomer unit ethylene, CH2 double bond CH2 or NCH2. This is the basic unit. 2 hydrogen atoms will be replaced by 2 fluorine atoms. So the starting compound or the monomer will be fluorinated ethylene or fluoroethylene. CF2 double bond CF2. When polymerized means, so this polymerization is obtained by water emulsion polymerization of tetrafluoro, 4 fluorine are present. So tetrafluoro and one unsaturated bond olefin is present. So tetrafluoroethylene under present in presence of benzoyl peroxide catalyst. So catalyst is always important. Or instead of benzoyl peroxide, you can use persulfate as an initiator. Through instead of water emulsion polymerization, you can use radical polymerization. Persulfate will initiate, produce a radical, and it can initiate the polymerization. So that will be free radical polymerization. This is the structure of Teflon. Fluoride groups are always hydrophobic. That's why this material is highly hydrophobic. Now let's take the synthesis addition polymerization reaction. Now here, look at here. No simple molecules are removed, just adding up. That's why the molecular mass of the monomer and polymer will be same. Polystyrene, Let's take again the well-known ethylene basic unit, and one hydrogen you have to replace with CH double bond CH2. Again, this is ethylene one. Instead of here, you are having CH2 double bond CH. Now, one hydrogen you are replacing with the benzene or aromatic ring, that is called styrene. Then you are reacting with an anhydride, which is CO2O. Phenyl anhydride means C6H5, phenyl group. C6H5 CO2O. Initiator you are putting 60 degrees Celsius, no pressure required, 60 degrees Celsius heating. You will get polystyrene where this CH double bond CH2, the unsaturated chain will grow along this one, and the styrene units will also be repeating. Again, the polymer will be having same molecular mass as the monomer. Thus, no groups are eliminated. Polyvinyl chloride, this is one of the important polymer. So vinyl chloride is the monomer for simple polyvinyl chloride. So vinyl chloride is the monomer for PVC, and the monomer is produced by direct addition of HCl to acetylene. So acetylene is an alkyne molecule. Similar like we have seen olefin, that is CH2 double bond CH2. Here we are taking CH triple bond CH, and then you react with hydrochloric acid HCl in presence of mercurous chloride, HgCl, and then it will react to form addition reaction. This hydrogen will add up here, this Cl will add up here, CH2, then triple bond will become double bond, CH2 double bond CHCl. Then if you take n number of n units of this NCH2 double bond CHCl, that is chloroethylene, then if you polymerize it, you will get this vinyl. So vinyl chloride you are taking n moles of vinyl chloride, you are doing polymerization, you will get poly n moles of poly vinyl chloride. So you will get polyvinyl chloride, CH2 CHCl n. Now let's move on to polypropylene. Polypropylene is obtained by polymerizing propylene. From the name itself, you can say vinyl chloride is the monomer unit for polyvinyl chloride. Propylene is the monomer unit for polypropylene. So propylene you already know is an olefin. 3 carbon is a propane. So when you have a double bond between the first and second carbon, it is propene, 1 propene, that is propylene. And now you polymerize it. This will become single bond. Double bond will become single bond. N molecules, if you are taking means you will get N polymer. So here is a special type of catalyst that is called Ziegler-Natta catalyst. So in MCQs they can ask this one: titanium trichloride TiCl2 plus diethyl chloroaluminate. So Al C2H5 Cl. So this composition is called Ziegler-Natta catalyst, or TiCl4 plus Al C2H4 triethyl aluminum or diethyl aluminum chloride. Either way you can say Ziegler-Natta catalyst. Properties, as I told, the reaction you can write, but properties and uses you have to write. So the properties of Teflon, it has highly electronegative fluorine atom, Cf to Cf2. So it provides strong interchange forces, high mechanical strength. It can be machined and molded applying high pressure, like a tape. Teflon tapes we know. And then uses of Teflon, it is the widely used insulating material which is used to insulate motor, transformers, cables, wires, etc. If you see an electrician, in his kit bag, always he will be having a Teflon tape inside it to tape the cables, wires, and etc. And used to make non-stick cookware coating. Tawa, the dosa tawa is made of Teflon coating, so it is non-sticky. Non-sticky tawas, no? The pans, all are made of this Teflon coating, and used for making gaskets, cooker gaskets. That is also having like Teflon coating. Otherwise, in water and steam, high pressure, then it can melt. So that is the reason they are using Teflon coating. Pump parts, many pump parts are made. Tank linings, pipes, and tubes for chemical industry and non-reactive coating. And properties of polystyrene, it is also a hard, transparent, stiff resin, widely used plastic, solid at room temperature, but it can flow which means it melts and flows when heated above 100 degrees Celsius. This is the melting point of polystyrene. It is insoluble in water, but it is soluble in organic and chlorinated solvents, and it is non-biodegradable. Uses of polystyrene, it is widely used for packaging, food service industry, and also it is used to make non-stick cookware coating, making rigid trays, containers, disposable eating trays, bowls, etc. And properties of polyvinyl chloride: it is colorless, odorless, non-flammable, and chemically inert powder. And we know the use of PVC pipes. And it contains 53 to 55% chlorine, and it softens above 80 degrees, like polypropylene. 100 degree above, this one 80 degree above. Resistant to water, light, air, and is highly chemically inert. Inorganic acids and alkalis soluble in hot chlorinated hydrocarbons. Uses of PVC or polyvinyl chloride: widely used plastic used in making cables, hoses, toys, raincoats, pipes of petroleum industry. It is also used in making floor, cover, tires, cycle, and motorcycle mudguards. And the properties of polypropylene: isotactic, highly crystalline, lightest polymer, resistant to chemicals, hardness and strength, high moisture proofing quality. And is also used in making ropes, carpets, blankets, bags, apparels, used for making packing pharmaceuticals and cosmetic products. It is also used for making hospital equipments, washing machine parts, pipes, furniture, etc. So with this, I would like to stop this lecture. In my next lecture, I'm going to teach you about the condensation polymers and examples of condensation polymers, their reaction types, and the properties and uses. Thank you for watching.